Have you ever stopped to think that the Earth might actually be, well, humming? Not the big shakes of an earthquake, but something steadier, deeper?
It sounds a bit strange, doesn't it? But yeah, there's this deep earth hum.
And for scientists listening closely, this isn't just background noise. It's maybe a clue, right?
Right.
A way to map out hidden plumbing systems like magma channels way down below.
Exactly. That hum, or the signals related to it, often comes from something specific, crockless waves. Some just call them crack waves.
Arc waves, okay.
They're these really slow, guided waves. They travel along cracks like fractures or dikes, but only if those cracks are filled with fluid. Could be water, gas, magma.
The sources used a great analogy for this, like an organ pipe underground.
That's a perfect way to picture it. Sound waves get trapped in an organ pipe, they resonate. Same idea here.
Mm-hmm.
These waves get trapped in the fluid-filled cracks, they vibrate, and they produce specific tones. These are the resonant frequencies.
And if we can measure the tune?
We might figure out the shape and size of the instrument, the crack itself.
Okay, so that's the mission for this deep dive then. We're looking at new research that helps us do just that, but for the really messy, complex crack shapes you actually find in nature.
Right, because nature isn't made of perfect rectangles.
And this is crucial for understanding things like very long period seismic signals, VLP signals, those really slow wobbles, like 2 to 100 seconds long.
Yeah, the kind they've been seeing at places like the Fani Maoré Submarine Volcano near Mayotte. We need better tools to decode those signals.
Moving beyond the simple textbook models.
Definitely. Into the real world, computationally speaking.
Okay, let's back up slightly. Why are these crockless waves, these resonances, so fundamental? What do they really tell us?
Well, their practical value is huge. These resonances happen because the fluid inside the crack is pushing against the solid rock around it, and the rock pushes back. It's a mechanical coupling.
Ah,
So the frequency, the tune we measure, is directly tied to the physical properties of that crack. Its geometry, size, shape, and the fluid properties too, like how dense or gooey the magma is.
stuff we just can't see directly.
Exactly. It's
Yeah.
like getting a peek underground without drilling.
So if these waves are like an internal probe, where is this technique being used?
All over geology. For us today, the big one is volcanology, interpreting those LP, long period, and VLP signals.
At places like Mount Redoubt or Etna?
Precisely. You need crack wave theory to make sense of magma movements there.
And I guess the fluid in a volcano can be pretty varied. Hot gas, thick lava.
Absolutely, and the physics has to account for that difference. But it's not just volcanoes. Think glacier hydrology.
Glaciers. They hum, too.
They do. These sort of humming signals people record,
Huh.
often attributed to crack waves in water layers under the ice.
Oh, okay.
And even, say, in hydrocarbon reservoirs. Energy companies use similar ideas to map out fractures where oil and gas might be trapped.
So volcanoes, glaciers, oil fields, it's a widespread mechanism.
Mm.
But if we've known about these waves since, what, the 60s, why the big focus now? What was holding things back?
The roadblock was really computational. Complexity. The math we could solve easily, the analytical solutions, they only work for super idealized cases.
Like infinite cracks or perfect rectangles, things you don't actually find.
Exactly. When you try to model real shapes, maybe branching networks, using computers, the calculations just became enormous. Too slow, too expensive.
Because you had to model the entire 3D chunk of rock around the crack.
Right. Simulating that full 3D volume was the killer.
Okay, so that brings us to the breakthrough. This new hybrid numerical method. How did they get around that 3D problem?
This is the clever part. They combined two existing methods in a smart way. The boundary element method, BEM,
BEM, okay.
which is great for modeling the response of the solid rock, the elastic part, and they coupled it with the finite volume method, FVM,
And FVM handles.
the fluid dynamics inside the crack, the acoustics, how the pressure waves move in there.
Combining two complex methods sounds, well, complicated. What makes this hybrid approach efficient? How does it tackle, say, a whole magma network?
The efficiency boost comes from a crucial shortcut. This is really the key. Instead of modeling the whole 3D volume of rock,
Which was the bottleneck before.
right, they realized they only need to focus on and discretize the crack surfaces. Just the 2D boundary between the fluid and the rock.
Wait, just the skin of the crack, not the huge volume of rock around it.
Exactly. BEM is perfectly suited for that, problems defined by boundaries. By switching from a 3D problem to essentially a 2D surface problem, you massively cut down the number of calculations the computer needs to do.
The degrees of freedom, right?
Precisely. It makes previously impossible calculations feasible.
That's a huge difference. Okay, so the model setup is efficient. How do they actually find the resonant frequencies?
They use something called eigenvalue analysis, and they do it directly in the frequency domain.
Not simulating it second by second in time.
No, and that's important. Working in the frequency domain lets you find the natural vibration modes directly. It avoids errors that can build up if you're simulating things over long time periods.
Got it. Efficient model, direct frequency calculation. Now, the researchers used two key numbers, dimensionless parameters, to describe the physics. Let's break those down.
Sure. The first one is pretty intuitive. Aspect ratio, which they call alpha. Alpha. It just describes the shape is the crack, long and skinny, or more like a square.
Simple enough. Aspect ratio. What's the second one?
The second is crack stiffness, labeled Telleller. This one's a bit more technical, but really important physical.
Crack stiffness. What's the core idea? How stiff the crack is?
Sort of, but it's more about how much the rock around the crack yields when the fluid pressure changes. It compares fluid stiffness to rock stiffness, scaled by the crack dimensions.
Okay.
The main point is, crockless waves, the slow crack waves we're talking about, really only happen when this crack stiffness, Telleller, is much larger than 1.
Tell needs to be high.
Yes. High stick means the crack is relatively compliant, the wave travels slowly, and you get these characteristic resonances.
Okay, so shape, alpha, and stiffness, stiffness. With the new method ready, what did they find when they systematically played with the crack shapes?
Well, they confirmed you get the simple modes you'd expect, like vibrations along the length or across the width. But in more complex shapes or networks, they saw these really rich vibrational patterns, much more complicated.
And what about changing the aspect ratio, alpha, making the crack longer and thinner?
That had a huge effect, especially on what they call mixed modes vibrations that involve movement in both directions.
How huge?
Well, for one specific mix mode in a rectangular crack, they found the frequency jumped by almost 15 times 14.6-fold, just by making the rectangle 10 times longer than it was wide.
Wow, just by stretching the shape.
Yeah, it shows how incredibly sensitive the frequency is to the exact geometry. Get the shape wrong in your model, and your predicted frequency could be miles off.
That really drives home why you need accurate geometry. Did they compare simple shapes like a rectangle versus an ellipse?
They did. And interestingly, the elliptical cracks always had slightly higher resonant frequencies than rectangular ones of the same overall size and aspect ratio.
Why is that?
The thinking is that the ellipse, because it tapers towards the ends, is just inherently a bit stiffer structurally. A subtle geometric effect, but measurable.
Okay. And the other key parameter, crack stiffness, $6. How did changing that affect things?
That showed a very consistent trend. Increasing $6 always decreased the resonant frequencies for all modes, all shapes.
Why decrease?
Because higher dollars link to slower crockless wave speed. Slower wave, lower frequency, it all ties together.
Right. So the systematic work built confidence in the model. Now, the real test, applying it to that puzzle at the Mayotte volcano.
Exactly. The Mayotte situation is perfect. This seismic crisis starts in 2018, leads to a whole new submarine volcano, Fani Maoré.
And critically generates these really weird VLP signals, right? Sustained, very oscillatory.
Yes. And when seismologists analyze those signals, stacking them up to get a clear picture, one thing really stood out in the frequency spectrum.
What was the puzzle?
You could see multiple resonant peaks, clear modes, but they were unevenly spaced. And the killer detail was the ratio between the first two big peaks. It was about 2F17, approx $2.55.
2.5? And that's weird
But
because
simple shapes, your standard rectangles or ellipses, usually give you frequency ratios that are much cleaner numbers, often integers like 2 or 3, or simple fractions. Getting 2.5 isn't straightforward.
So before this new method, how would you even try to explain that 2.5 ratio?
You'd have to invoke some special pleading, maybe mode skipping, perhaps the fundamental mode, F1, was actually excited, but for some reason it just wasn't recorded well.
Or the sensor was in the wrong place.
Or the seismic source happened to be on a dead spot, a nodal line, for that mode. Possible, but it requires pretty specific, maybe unlikely, conditions.
Okay, so the new hybrid method lets you explore more realistic shapes. Did they find a geometry that naturally produces that 2.5 ratio?
They did. After testing various complex geometries, they found one shape that nailed it, a dumbbell-shaped crack.
A dumbbell. Like wider at the ends and narrower in the middle.
Exactly. That specific shape, with its varying width, naturally produces resonant modes, where the ratio between the first higher mode and the fundamental is right around 2.5. No mode skipping needed.
That's incredible. You've potentially heard the shape of a magma chamber miles down.
It's strong evidence linking those VLP signals directly to the resonance of a specific complex structure.
Amazing. Okay, one more piece here. The modeling focused on the resonance itself, but in reality, energy leaks out, right? Damping. What about the quality factor, Q?
Right, damping is crucial. It controls how sharp those resonant peaks are. If damping is high, Q is low, and the peaks get broad and hard to distinguish.
What causes damping in these cracks?
Two main things the researchers considered. One is simple friction, the viscosity of the fluid, like think magma rubbing against the crack walls. The other is seismic radiation energy, escaping the crack system entirely as seismic waves traveling out into the rock.
Let's take viscosity first. How well can we model that damping?
Well, there's a classic, very simple formula for viscous damping. POCU, where zeta relates crack width to a viscous boundary layer. It was originally derived for an infinite crack.
A simplification. Does it work for real finite cracks?
Surprisingly well, according to their tests. They found it's a rather good approximation even for a finite rectangular crack, pretty much regardless of aspect ratio or which mode you're looking at.
That's useful.
It really is. It suggests maybe we can calculate the main resonance frequency with the fancy BEM plus FVM method, and then just use this simple formula to estimate the viscous damping afterwards, even for complex shapes like the dumbbell. It saves a lot of computational effort.
Okay, so viscous damping might be simpler than we thought. What about the competition between viscosity and that other loss mechanism, seismic radiation? Energy shaking the earth versus energy turning into heat in the fluid.
Yeah, they looked at that trade-off. Turns out the balance between radiation damping, RD, and viscous damping, VD, depends on a few dimensionless numbers, including that crack stiffness, $2, and the viscous parameter zeta.
And is there a condition where one clearly wins out?
Yes. They found that when the viscous boundary layer is thin compared to the crack width, so high zeta, and the local crack stiffness is relatively low, seismic radiation dominates. Most of the energy loss is from waves escaping into the surrounding rock, not from fluid friction.
And that's important because
It means the seismic signals we actually detect at the surface are likely a pretty efficient radiation of the energy resonating the crack. The signal isn't just getting muffled and lost as heat down there, it's actively getting out.
which gives us more confidence that the signals we record really represent what's happening in the source.
Exactly.
This has been a fantastic deep dive. It really feels like we're moving into a new era of understanding volcanic plumbing.
I think so. The big takeaway for me is that we're breaking free from those oversimplified models. We're not stuck thinking about simple boxes or tubes anymore. We can take a weird specific signal from a volcano, like that 2F11 ratio of 2.5 at Mayotte, and use these advanced computational tools to link it credibly to a specific complex shape underground. That dumbbell crack, for instance.
Mapping the Earth's tune to its hidden geometry. It's revolutionary.
It reminds me of that old mathematical question Mark Kulikak asked. Can one hear the shape of a drum?
Can you?
Well, mathematically, strictly speaking, the answer is no. You can have different shapes that sound exactly the same isospectral drums. But
But in geophysics, maybe it's different.
maybe. Because we have more than just the frequencies. We have the pattern of modes, the damping, other seismic data. So the provocative thought I'd leave you with is, with these new modeling techniques, how close can we get? Can we eventually map out the entire topology, the full interconnected network of cracks under a volcano like Mayotte, just by listening carefully?
That is quite the challenge. A fascinating place to leave it. Thank you so much for sharing all this.
My pleasure. It's exciting stuff.
Absolutely. That's all the time we have for this deep dive.